As you've guessed from my accent, I'm Italian. No, I'm joking. I'm from London. I work at a travel startup there called Duffel. If you like holidays and really clever and kind people, you can also work there too, because we're hiring. So you can follow me on Twitter if you want to see me rant at businesses for doing things wrong, or you can follow my blog that I barely update as well. So today we're going to be talking about pattern matching, and I'm asking this question: is it good in the abstract? So when you first start Elixir, you see something like this, and you're like, cool, I know what that does, right? And then you see this, and you're like, hang on, that's backwards, right? And the reason is, it wasn't variable assignment that you saw, it was pattern matching, right? And it's a brave new world. Pattern matching is an abstraction around two things, right? It's like variable binding and control flow. And the idea here is that if a pattern, you have a pattern that you match against some data. If it matches, you can bind 0 or more variables. So that means that those variables become available in the scope that you're in. But crucially, if the pattern doesn't match, then you affect control flow in some way, right? So that maybe you raise an exception, or maybe you fall through to another case. It kind of depends on the context of where the pattern matching happens. So you've probably all got some great examples in mind of where you've used pattern matching, and it kind of like helps simplify things. So this is like a simple FizzBuzz implementation. And what I find kind of interesting about this is, if we kind of compare it to an implementation of the similar idea, which doesn't use pattern matching, and again, it doesn't really matter about the details of it, you can just get a picture from the shape of the code, like that when we use pattern matching, we had like a much flatter kind of structure than what we do when we don't have it, right? And here's another example from in Elixir itself. This is how reduce is implemented. And again, it's not important that you kind of read and understand all the code that's on there, but let's look at a version that doesn't use any pattern matching, and once again, you can see the shape is like a lot more nested. So there's this property of pattern matching that kind of like flattens out conditionals, which I'm claiming at least helps like us understand the code a little bit better, which is cool. Here's another example. This is getting the best friend's name, but only if the user is an admin. So what I like about this is it's creating a picture of the data that we're matching against, right? And more than that, that picture is drawn with syntax. It's like the same syntax that you use to construct the data, right? So construction and destruction use a very similar syntax. And what I mean by that is, if you know how to draw like a literal map in Elixir, there's a good chance you're going to understand how, like what a pattern looks like as well, because they're very similar, right? So a pattern is this picture. It encodes a lot of information, and kind of construction and destruction are the same syntax. And that there is also like another kind of related idea here, which is that if we try and imagine how we would get the same kind of data without using pattern matching, we'd probably use functions, right? And you have two options there. One is to define like quite a specific function, something like my best friend's name, right? And that feels like that's going to bloat the API surface area of user a little bit, because it's like overly specific in some way. The other option is that you define more functions that you kind of compose together. And so all of those can have like trade-offs, whereas like you can see with the pattern matching, you can get quite a succinct and like informationally like dense, I guess, picture of what's happening. Yeah. And the other thing is that when you look at this, you understand what's actually happening, right? There's no abstractions here. You know that user has an admin key on it, that friends is a list, you know, and that they have friends and that's a list. And you get a real good sense of what user actually looks like, at least in some of the cases, right? Cool, so we love pattern matching. I'm sure you do too. You've probably used it everywhere. But there is a problem with it. We don't talk about it too much in the Elixir community. So this is the pipeline operator. If you've used Elixir for more than about 4 seconds, you probably know what this is. And it's kind of a rite of passage in Elixir, I think, to take it upon yourself to improve this, right? So I'm no exception. I did the same. I've written a pipeline library, and here it is. The idea here is that pipelines have some state. You thread that state through steps in the pipeline, okay? So here, you know, we start with 1, we can add 2, we can times 3, it's all looking good. Now, it's probably a separate talk as to whether or why this might be a good idea, but, oh, yeah, just behind the scenes, this is kind of what's being created. So we create a struct that has the steps in them. The steps have actions, right? Now, so what's kind of cool about this is you can define then executors for that function, right? And so one such executor we might want to define is something like with trace. Now, there's a lot of code on here, so don't try and read it all, but if we break it down, it's quite simple, right? We get the steps out of the pipeline. We get the state out of it. If there are no steps, just return the state, we're finished. If there are some steps, get the current step, execute it, and then if we error, bail out now, don't continue with the rest of the pipe. And if there's not an error, continue with the rest of the steps, updating the state as you go, right? But then what's cool is you can now add logging in between, like before and after that step runs, right? So you might add some logging before and logging after that times how long it took to execute that step, which means you get in this situation where you can really easily add tracing to your Elixir functions by just like making a one-line change, which is kind of cool, right? So great, you deploy that, you get it going, everyone loves it, and you're a hero, it's fantastic. Then what happens? Features with a capital F, right? The next thing people want is undo and rollback. So if you've ever used Sage or heard of the saga pattern, this is that, right? So the idea here is that one of your steps in the pipeline can fail. When it fails, you want to run a compensating action for that step to kind of like undo it conceptually. And then you want to step back through your pipeline, running an action like an undo action for each of those steps that has already been run, okay? So to get this going, we have to do 2 things. First of all, we add an on-error callback. That's like, oh, your pipeline's failed, let's undo. So we -2 instead of adding it. And then the next thing, we take our pipeline, we take what was the list of steps from that to this. So this is a zipper data structure, okay? And the idea here is that that left-hand list you can see are all the steps that you haven't executed yet. And the list on the right are all the ones that you have. And so once you've executed a step, what you do is take the head of that left list and prepend it onto the right-hand side there, and you move it across. And what that means then is if you do need to step backwards, you haven't lost any information like we had before, and you can just get the head of that right-hand list and move it back again, and now you're back at step 1, right? So what effectively ends up being true is that like that head of the left list is always the current step you're on, and the head of the right-hand list is always the previous step. Cool, so feeling pretty clever, you know, you deploy that, everything's looking good. But what's happened? We've broken our with trace function because now this pattern match doesn't hold true anymore, right? And you might be thinking like, oh, just like chucking a guard clause, and it doesn't really solve the problem, right? It just gives you a different error, because still our function doesn't do what we want it to. And the problem here is that pattern matching doesn't get on with abstract data, okay? So what is an abstract data type, just to be clear? So abstract data is a data type where you can think of multiple implementations of like this abstract idea. So for example, let's think of list. List is like an ordered collection of stuff, yeah? There's many ways we can think of implementing that. For example, arrays, where all of the stuff's in like a contiguous block of memory, or like linked lists, fixed size vectors, you know, all sorts of stuff. So you can imagine more than one implementation of the abstract idea. Like another example would be shapes. If you think of shapes as being things that have perimeter and area functions, you could have square, circle, triangle, right? And finally, our pipeline is an example of abstract data because we can imagine having pipelines and reversible pipelines, yeah? And it's kind of like a key thing about these abstract data types is that you can imagine having concretions that vary over time or vary at the same time. So what I mean by that is you can imagine a programming language that lets you have arrays and lists, or arrays and linked lists at the same time. Or like our pipeline, maybe it just evolves its implementation over time, right? And you have to be able to handle just one thing, but you have to be able to handle it changing over time. Cool. So why does pattern matching not like abstract data? Well, abstract data is trying to, by definition, hide details from you, right? Whereas pattern matching is trying to expose them. So I know what you're thinking. No? I'm proud of that reaction, if I'm honest. I know what you're thinking, and it wasn't, it's, you just add more functions, right? So you add a next step, a previous step, a current step into the pipeline, and then you change your with trace function. And all we do now is call the pipeline module and hide loads of implementation details in there. Cool, so then that means if, the pipeline implementation changes, you can change it in one place and nothing else breaks in your system, right? And that's cool, that's probably what I would do, to be honest. But it just leaves me thinking, what are we saying here? Are we saying, never use pattern matching then? I don't think that goal is really something that Elixir is going to help you with. And I don't think that's what we are saying when we do that. So it's is pattern matching only good in this abstract sense, right? The question I want to ask is, can we bring them together? Can we get the best of both? Can pattern matching be good in abstract data types? So there's two ways we can do this, right? One is we can make abstract data more direct in a sense, okay? The other is we can make pattern matching more indirect. So what do I mean by the first one? Well, the claim I was making that one of the benefits of pattern matching is that it shows you actually what's happening, right? Peers behind that abstraction. So it's can we bring that to abstract data without sort of losing the abstraction, yeah? And kind of the only way I could really think about this was more in the developer tool space, and I think it's an important thing to talk about. Often we think about design patterns and way to structure code and architecture, and they're all really important. But I think we often forget that we can write things to help us write programs, right? And so I was just imagining what if we okay, when you are writing code, it stands to reason that you want to do different things maybe from when you're reading code. And what's good about this abstraction is when you edit the code, you only edit one function and it applies everywhere, right? But that's not as helpful when you're reading it, where you maybe want to see what's actually happening. So I was kind of what would happen if you could hit a hotkey and just flash up the pattern match that's being used kind of thing and see, oh, a zipper's being used in that case or whatever. I don't know, maybe your editors already do this, but mine definitely doesn't. I just thought it was kind of interesting to think about. Cool, so that's sort of more direct abstract data. What about the other one? So can we bring indirection to pattern matching? So the key to this is we want one pattern to work on multiple different data types, okay? And again, there's two ways that we can kind of get that. The first we can already do in Elixir, okay? Because all structs are maps, okay? Any valid map pattern is a valid struct pattern, which you can see here. We've got on the left one pattern that's being used for two different data types, a bare map and a user, right? So in this sense, you can abstract over these data types we're matching on already with one bit of with one pattern. But there's kind of a big limitation here, which is that it forces your abstraction to be expressed structurally, which means via the keys that are being matched on, right? And you can kind of see this, imagine we define an area function that wants to take in any sort of generic shape and call area on it. We'd have to put area as a key in that. And there's a place for this kind of abstraction, but it can also be limiting. Consider this. We can have two different kinds of colors, right? RGB and CMYK. And the problem here is there are no key overlaps here. None of the keys are the same between them, which makes it a lot harder to abstract over them and say I don't know, is the color red, right? Because there isn't a thing you can look at that's common to both of those data representations. Now, you would probably do this, right? You just get the struct name out of it and kind of call a function on there, and that's fine, but that is a structural abstraction. You're saying what's common about those two data types is that they have a struct name, right? So it can be limiting is the point. Okay, so then what's the proper way to get one pattern to work with many data types? Well, re-implement pattern matching, of course. Now, don't get excited. This isn't production ready or anything, but I'm certainly not brave or clever enough to attempt to re-implement Erlang's pattern matching syntax, but I am foolhardy enough to try it in Elixir. So I wrote a little library. Let's try and step through it and see if we can get an understanding of what happens with it. So the first thing we need is like a pattern syntax, yeah? So the top line is the valid Elixir that we all know and love, yeah? The line below is what we're going to use as our patterns right now. So it just says var and then current step, which is the name of the var, and then rest is stored in a variable called rest, okay? Now, because we're writing this in Elixir, like, we can't overload this equals operator, unfortunately. So we get kind of close by defining our own infix operator here, okay? And again, because we're implementing it in Elixir, we kind of have one arm tied behind our back here. Elixir can just pattern match and makes variables appear in scope like magically. We don't have that luxury here. So we have to return an explicit map of variables that came out of the match that we're doing, right? So a bit more verbose, but it's tolerable. Cool, so what does that infix operator look like? It just looks like this. So we call this like magic function here, which I guess we'll get to in a second. And if there isn't a match, we raise an error. And if there is, we return the bindings that were made out of it, right? Cool, so what's that? That is a protocol. So if you don't know protocols in Elixir, they're a way of defining one or more functions that take one or more arguments, right? And they let you define new implementations for those functions for each different data type that you have, which is the exact problem we were trying to solve, right? So we define a protocol, and then we can separately define an implementation for it. So in our case, we could say, look, if the first argument that we're like pattern matching on, if the data we're pattern matching on is a list, this is what you should do, okay? So to actually do like a simple implementation then, this var function that we saw earlier in our pattern syntax returns something that looks like this, okay? And that means then, in our pattern match, like implementation of the protocol, we can, this is a case where the data you're matching on is a list of one item, okay? And the pattern is a list of one variable, okay? So what this does is it just gets the variable name out, puts that into the map as the key, and then puts the value of the, the item that's in the list as the value. So you end up with a variable of whatever the name was, which is the item in the list, right? And conceptually, you can imagine doing all the rest of the implementation, drawing the rest of the owl, if anyone's seen that meme. But cool. Well, what this means then is that if we go back to our pipeline operator, remember we had the steps, and we turned it into a zipper. Well, we could like wrap this into an actual struct, right? And then that's going to allow us to implement match for zipper differently, okay? And there's lots of ways we could do this, but like maybe we're like, look, if you've completed it or not, it doesn't matter. If it's got one element in it and your pattern has only got one var in it, then it's a successful match, like, and away you go. And we can imagine adding more cases for all the other, edge cases below, right? Cool, so if we go back and edit update with trace, this is what that looks like. And it looks pretty close to what we had with the pattern matching, right? It's not a million miles away, and especially if we improve the syntax a bit, you'd probably get a good gist of what's happening there. But yeah, we just access the bindings that get returned, and kind of like that's the result of it. So what's really nice about that then is we've got this function now that can handle both pipelines and reversible pipelines in the same way. And what's even cooler, right? We implemented pattern matching with pattern matching, which is just a bit fantastic, if you ask me. But it actually led us into a problem. And to see the problem, let's consider what we might try next, which is allowing extensible patterns. So we want to allow users to be able to define their own patterns, okay? Now, the first step to doing that is using more protocols, which we're going to get to in a moment. But the first change that we have to make to allow this feature, okay, is we need to change what this returns, okay, from being a tuple to being a struct. Okay, and the clever people among you probably have already realized what's happened. This pattern match now fails. So conceptually what we've done, right, we've changed an implementation detail of like some abstract idea, which is like a pattern. Doing that has invalidated a pattern match, which means we run into the problem that we're trying to write the library to solve, which means we need the library to be able to write the library. It's like you have to go and have an ice cream and sit down and think about your life and probably throw the computer out the window. So what's the solution? Well, it's not pretty, but let's step through it. So the first thing we need to do is understand the problem, okay? So we have pattern syntax like variable, okay? And that's like a top level pattern, you could consider it, because you can just assign, you know, a value to a variable. That's a pattern. But variables can also, you can have like higher order patterns in a sense, right? Patterns that have patterns inside of them. So the list pattern below is an example of that, because it has variables inside of them, right? And you can have lists that have lists inside of them, right? So the problem is, variable outside of a list is actually a different pattern from variable inside a list. And the reason is the index, right, the position that the pattern is in the list is important. And to see that, you can look at this example, right? The top line matches, and the second line doesn't, because there's no bit of data where B is in the pattern, right? So when you're outside, when you're a variable at the top level, like you can just match anything. But when you're inside a list, it's important to know what index you are, to know, oh wait, in that data, is there something at this index that I can, is there a value there that I can save, right? And furthermore, across different kind of higher level patterns, if you will, different things matter, right? So in the bits below here on the maps, you can see it's not an index that's important when you're a variable, it's the key of the map, right? So the bottom line doesn't match because there isn't a key A in the map that we're matching against. So for list patterns, index is important. For map patterns, keys are important. You can imagine other patterns where other things are important, okay? So to be able to enable these extensible patterns, what we need to do is three things. We need to be able to add new top-level patterns, one. We need to be able to define how those top-level patterns behave inside other patterns, okay? And finally, we need to be able to implement both kinds of those patterns differently for different data types, okay? So the first step is to make the pattern structs, as we pointed out. What that essentially means is where we used to have that top line, it becomes something like the bottom line, and it returns something that looks like this. So this is the list pattern, which has patterns, and then you can see what the patterns are, right? Cool. The next thing we're going to do is actually swap the argument order of the match protocol. So this is the protocol that we had before, and we were dispatching on the data type. Now we're going to dispatch on the pattern. And what this has done is given us a seam, right? Because now we can add new top-level patterns by implementing this for them, okay? But the tricky thing is, we still need to be able to add implementations for this data as well, right? What we kind of need is like double dispatch. We need to go and find the implementation based on the type of both of those arguments, not just one of them. So to get that, we have to like start calling protocols within protocols, and it gets a bit mental. So again, lots of code here. Let's try and step through it a little bit. This is going to be our list pattern implementation of the match protocol, okay? So the first thing we do is we get those patterns out. That's the list of patterns that you have, okay? And we reduce while over it just so that we can bail out if we have a match error earlier. And then this is our accumulator. And the accumulator is a little weird. The left there is the index of the pattern. And the reason we have that is because, like we said before, the index is important when you're matching lists, because you need to be able to say, in the data, was there a value at the index where the pattern is, right? And then the right-hand side of that tuple is just the bindings that we're accumulating up. So they're the variables that we add into that map as we find matches. So yeah, that's just showing you that. Cool. Okay, so we call this function list pattern.match, which I'm going to come back to in a second. But like conceptually, it's like if we get a match, we just increment the index and like continue on, and if we don't, we bail out, and then this bit just like unwraps and or raises an error if there's a match error. Okay. Okay. So what's this function then? Well, this is another protocol. So this, let's look at the function signature here. So the first argument is a pattern. And what that allows you to do then is implement list pattern differently for different patterns. Okay. So effectively what that is allowing you to implement how a pattern should behave when it's inside a list, okay? Which means that you've got flexibility to not only add new patterns, but add behavior for how they act when they're inside of a list pattern. Cool. You've got the data, which you're obviously matching on. You need that. The bindings, where like if your pattern is a variable, for example, you'll want to add to those bindings. So you'll need them, and the index for the reasons we've already mentioned, right? Cool. So you make this, which is cool, but there's a problem because we've already defined this pattern to be a struct, right? But what's kind of cool is you can just do that, right? Like Def Protocol returns a module, so you can just make it a struct if you need to, and kind of everything works out, which is cool. So let's implement this then. So this is implementing list pattern for variable. So what this is saying is, imagine you have a list as your pattern, and the first thing in it is a variable. This is what's going to run in that situation, okay? So you might be noticing a pattern. Variable in a list is a protocol. So again, if there is a match, we update. What that is going to return, right, is the data that we accessed. So it's going to try and access some data in the data that we're matching against, okay? And if it finds something where it should, like at that index, it's going to return it to us, which is what that value is. So effectively, if we get returned the value, we can update our bindings with the variable name that we're using, okay? And if there isn't, there's no match. Okay, so why variable in a list, and like kind of what does that mean really? So yeah, so I guess to think about why it's called like variable in a list is because by the time we get here, that's what we know we are. It's a bit strange, but yeah, I guess I'm just going to skip that bit for now. But here's that protocol there that gives us a way to define how a given bit of data should behave when you pattern match it against it with a list which has a variable in it, kind of thing. Cool. So if we actually implement this for a list, all we'll do is like fetch from the list the thing at that index, and if it is there, if it isn't there, return it, and if there's nothing there, then it's not a match. Okay. Cool. So a bit mental, but it does do what we kind of wanted. And to kind of demonstrate that, like let's try and implement a new pattern. Let's allow matching on zippers, okay? So to do that, all we do is implement variable in a list for zipper. So recall variable in a list is saying like, this is what should happen if I'm matched against by a variable that's in a list pattern, okay? And all we do here is like a similar thing that we did with the list. We just combine those two lists together, and then we fetch, and if there is something in that index, then it was a good match, and if there isn't, then it was a bad match, kind of thing. Cool. So all of that kind of buys you this here. So we could define a list and our zipper. We can have a pattern, and this pattern is like data now, so it can be stored, it can be saved as a variable and passed around, which is kind of interesting. And then we can finally do the matches on them, and both of those matches will return the same thing, which is a map of A to 1 and B to 2, okay? Which is kind of cool. And then finally, just to kind of demonstrate what you can do, like if we want to add another top level pattern, maybe like empty, we can do a similar thing. We define it as a protocol. We make it a struct so that we can implement it for other protocols, and we fall back to any, which we'll get to. But essentially, we define our match implementation for empty here, and all that's going to do is allow a data type to implement empty for itself, okay? which is like this. So in a list, we'd say, if I'm an empty list, then I've matched an empty pattern, okay? And if I haven't, then it's no match kind of thing. And the fallback to anything is we could implement it, a fallback which just raises and says like invalid pattern syntax. And that means that, it's not valid to use empty as a pattern on any other data type. So you might rely on this to, you wouldn't put empty against an integer, right? Because it kind of doesn't make sense. So if you fall back to if you match against data type that didn't implement the empty pattern, then you are going to fail and you're going to get like a decent error. And then you can also, implement map for empty as well, and you kind of end up with the same thing. Cool. So that might have been a bit confusing. If it was and you don't get it straight away, don't worry. Watch it again on YouTube. If you're watching it on YouTube now, hello. The question I have to ask, though, is is this good? Oh, so you were thinking the same. All right. Okay. Yeah. I mean, it was fun to write. So the original things we said we liked about pattern matching were patterns are a picture, construction and destruction had the same syntax, and you understand what's actually happening. Well, our syntax for the patterns has changed, right? So that's not true anymore. We've added indirection, which means from looking at a pattern, you can't tell exactly what's happening. And if you use what I just wrote, you probably couldn't tell what was happening even if you read the code. But so you kind of lost a little bit there, right? So the question is is the patterns as a picture enough of a benefit to make it worth having pattern matching on abstract data? I don't know, maybe, right? I could imagine a world where if we could tidy up the syntax, seeing something like this, in fact, let's step through an example. So imagine this is what we had, but the list implementation changes now. And let's imagine we change it to, map list, right? And so instead of an actual list, it's a map with numbers as the keys. And say that gives you better random access or something, right? The point here is, if you change that to be an abstract match, I still feel that this picture is telling you something about the data that you're looking at. Even if you don't know the specifics of it's not a list, it's a map list or whatever, you still get a very good gist of what's happening. So I think if you could fix up the syntax, maybe there's room for this. And also you could separate pattern matching on abstract data from being able to define your own patterns. I don't think they have to be together. So you could simplify some things. Cool. So is this mental? Have I just made all this up? Well, Clojure does a similar thing. Okay. So Clojure has core match. And in Clojure, you can pattern match on sequence abstraction. So you might have vectors or lists, and you can use a similar pattern to match on the same pattern to match on both of those, which is kind of cool. They have a really cool wiki actually, where they talk about the implementation that they've used and the paper that they used to speed everything up, to implement it performantly. F# also has these things called active patterns. Active patterns are an attempt to allow pattern matching on abstract data. It's destructuring this abstract data in a way that kind of makes sense. And again, there's a paper that you could go read if you were very, very bored. And Scala has extractors, which are kind of a similar idea, right? So is there a conclusion? Well, let's try and make a pithy kind of golden rule. I made a nice acronym here. So say it with me. So it stands for, if you are using pattern matching, then think about if you are crossing an abstraction barrier, and then maybe don't. If I was to sum it up, I would say if you're pattern matching on non-abstract data, go ham. Have a great time. If you're crossing a barrier, probably don't. Try and do that pattern matching inside the module, the abstraction itself, right? And then maybe a question for the community. Do we think abstract patterns are a good idea? Question for you. So I leave on a quote. I've seen this guy on the forum a few times. It's kind of, he must be active on it. And he says, for what it's worth, this is a question I frequently ask myself, is it worth adding abstractions on top of pattern matching? And I share this just to kind of express it's nice to know that I'm at the bleeding edge of Elixir thought leadership. So that's all I have. I don't know how we're doing for time because I didn't even start my timer. But if there's questions, why not? Like, cool. That means it was a perfect presentation. Yeah.
Have you used this in any projects of yourself?
No, it didn't make it through code review. No. Honestly, I haven't tried. So I think, but that's a good question because it's, it's a litmus test. Do I think it's a good idea? No. I think if we really wanted it, we'd have to implement it at the language level, right? But I'm not qualified to attempt that. So. All right. Thanks then, everyone. Cheers.